So you wouldn't have to always do this, right? Lighten this up a little bit, there we go. But I'm gonna work through this as though I could ask you any question about the information given. So I'm gonna write down even more than you would have to do maybe for some of these questions, but if I had asked slightly different questions, I'll show you the way in which you can answer any of them, right? So the first thing we're told is suppose given that someone is lying. So anytime we see this word given, right, let's think about that given, right, that someone is, wait, is this lying? Or do I feel like that's spelled wrong? Lying? It can't be right. With a Y, for sure. Not an English major, right? So given that someone is lying, right, the probability the lie detector test says they're lying is 90%. So lie detector says that they're lying is 90%, or probability of 0.9. Okay? So it's the very first thing we were given. Then it says, however, given that an individual is not lying, so given that somebody is not lying, the probability that the lie detector test determines they're lying is 20% of the time, or a probability of 0.2. Okay? So this is just directly what we were given. And then suppose that recent studies found that on average, people lie. So we'll kind of say this as probably they're lying. What, 5% of the time, or 0.05. Okay? So that was just what we were given initially. Right? Now in any problem, we can use these probabilities to find 3 other probabilities. Right? So the easiest one is probably, if the probability someone is lying is 0.05, the probability that they're not lying, right, there's only 2 things you can be doing, lying or not lying. So those have to add up to 1. So if we know the probability of, right, we can think about this as A, the probability of A complement, right, would just whatever gets us up to 1. Okay? The other things that we could determine, and this might be a little bit less clear, given that someone is lying, we know that the lie detector will show they're lying 90% of the time, which means that if we're looking at those same people who are lying, so we still condition on that same state of nature, the probability of the other outcome of the test, not lying, has to be, right, it's the only other outcome we can see for the test, so those 2 probabilities have to add up to 1. So if this one's 0.9, the other one would have to be 0.1. Okay? And then similarly, if we condition on the other state of nature, so that they are, given that they're not lying, the probability the lie detector test says they're not lying. Well, given that they weren't lying, the lie detector incorrectly said they were 20% of the time, or probably 0.2. So the remaining, right, to get us up to 1 would be the other outcome of the test. So the probability they're not lying would just have to be 0.8. Okay? So I can get these all on the screen here. There we go. So we may not need all these probabilities that I just kind of showed you how you could find, but if we did, I'm making sure that you know how you would do that. Okay? Any questions on that? Okay with that? Okay. So now let's start working through these problems, right? And I'll kind of have this on the side. I'll pull it up again if you need to kind of write those down again. You know, if you're watching this, but you could pause it. But for those of you who are here today, I'll be showing this again briefly. Okay. So question 10, I would always kind of approach these. Just write out what you're looking for. So that question 10 is the probability that a person is lying, and the lie detector test says they're telling the truth or not lying. Right. So what we're looking for here is the probability that somebody is lying, and right, the lie detector test says they're telling the truth, so not lying. Right? Because when we see a lie detector test saying that someone's not lying, well, there were some people that just slipped through the cracks, right? Some people who actually were lying, but the lie detector test didn't pick it up, right? Because this wasn't a 100% fail-safe test. So anytime we want to find the intersection of 2 events, we'll go to our formula sheet, scroll up, we've got this equation here, which is anytime we have the intersection of two events, we can rewrite that as the conditional probability times what we're conditioning on. So if we want to think about it as here is our A and here's our B, we can find the intersection by what? Taking the conditional probability of B, right? B given A is what that formula says right here. So the probability the lie detector says they're not lying, given A, our A is given that they're lying, and then multiply that by the probability of what we conditioned on, which was that the individual was in fact lying. Okay? Now from here, it's a matter of plugging our values in, right? Because we already determined these things earlier. So if we look back, well, it's not here, so we got to go all the way down here, so I have to cover this up for a second. But given that someone's lying, the probability the lie detector test said they weren't lying was 0.1. So we have that conditional probability, plug it in as 0.1. What's the probability that someone's lying? Well, that was just 0.05. So this should just be 0.005. Go back. Sure enough, that's answer A there. Okay. So all we did is once we had it written out, it was just a matter of identifying those things from what we originally had done and plugging those values in. Okay. Any question on that one before we kind of keep moving here? So then on 11, what's the probability that somebody is not lying and the test says they're not lying? Okay. So it's going to be a very similar problem. So now it's, what's the probability that somebody is what? Not lying. And, right, the test says that they're not lying. Okay. So once again, we can kind of think about this is our A, this is our value for B. Right. Make sure I just had an email come and make sure it's not about the link. Okay. So similar idea, we go back to that formula sheet. If I want to find the intersection of two events, I can use the conditional probability times what I'm conditioning on. So this is the same thing as event B. So that was that the lie detector said that they're not lying, given our event A, which is what that they are not lying, and then multiplied by the probability that they, or whatever we're conditioning on, for that event A, which was that they are not lying. Okay. So we've got it written out in the context of our example. So given that someone was lying, given that someone was not lying, the probability the lie detector said they weren't lying was 0.8. So just plug that value in here. Multiply that by the probability somebody wasn't lying, which we determined earlier was 0.95. Okay. So if we do that, well, we're going to get should be able to do this off the top of my head, but I can't. Oops. 0.76. Okay. So those two problems, we really worked them out the exact same way. They're just asking for slightly different probability, right? Slightly different things. But it's really the same procedure and the same formula here was used in either one of them. Okay. So what we get 0.76 here. Oops. I can highlight this. There we go. Any questions on those two? Those ones shouldn't be too bad. The next one's going to be a little bit more difficult. Right? The next one says, given that an individual fails the lie detector test, or basically it's saying that they're lying. So right away, what we're going to write out is, given that the lie detector test shows that someone is lying, right? That's kind of what we're told there. Then what's the probability the individual is actually telling the truth? So what's the probability that they're actually not lying here? And I'm just writing not lying instead of truth just so we kind of keep it consistent with what we did earlier. right? It's really just two different ways of saying the same thing. Well, if I go to my formula sheet, I might think that, okay, I'm looking for a conditional probability. I can rewrite this as the intersection divided by what I condition on. Now, the problem is if I think about what am I conditioning on here, it's the probability that the lie detector test shows someone's lying. And if I look at my original kind of probabilities, I don't have that, right? So anytime, you kind of notice the practice exams are following a similar format. And a lot of times, anytime you're asked for this conditional probability, if you're not using a contingency table, it's probably going to be that this equation, right, we don't have the probabilities to be able to use it. But if we broke them down, we would eventually arrive at this Bayes' theorem equation. And we can use that and just write it out in the context of our example. And then it's probably from there, it's just plugging in probabilities that we had from earlier, okay? So I'm going to write this out in the context of my example where this is my this is my S, and this is my E. I was thinking one step ahead. Okay, so the probability of S would be the probability that someone is not lying times the probability of E given S. So E was that the lie detector shows lying, given my S, which is that they are not lying, right? Let me zoom in a little bit on this because I know this red mark is a little bit harder. Oh, I'm going the wrong way. There we go. Okay. I then have to divide that by, well, now notice the very first part of my numerator is first part of my denominator is the same as my numerator. So, in the sake of not running out of room here, you could write this out again, but it's the exact same thing that we have up here in my numerator. So I'm just going to kind of remember that. Now, in practice, when you're doing this, I would write that out again. It's just here, I'm going to run out of room pretty quickly, and I don't want things to kind of look like a mess. I think this will help keep the second part more clear. So we've got that first part of our denominator. Then we add the probability of S complement. So our S is that they're not lying. So our S complement would be that they actually are lying, multiplied by the probability of E given S complement. So our E is the lie detector test shows they're lying, given S complement, which we just said, if S is not lying, S complement is that they are lying. Now from here, it's just a matter of plugging things into our equation. So what was the probability that someone wasn't lying? That was 0.95. So 0.95 multiplied by, given that someone's not lying, what's the probability the lie detector test shows they're lying? We had that up here, which was 0.2. Plug that in. Now remember that first part of our denominator was the exact same as up here. Okay. What's the probability someone is lying? We had that earlier. It was 0.05. 0.05. Times, given that they're lying, what's the probability the lie detector test shows they're lying? So given that they're lying, the probability the lie detector test shows they're lying was 0.9. Right? And now it's just a little bit of math, right? So now we just have to make sure we get this entered into our calculator correctly. And we get about 0.81 approximately, if I round that to the second decimal. Okay. So we go back here. Oh, I didn't round, I had it out to the third decimal here, sorry. We rounded to the third decimal, 0.809. Okay. I should have looked at those answers. Like I mentioned on Monday, whatever decimal the answers have, that's the decimal point you should be rounding to. Okay? Any questions on that? This is probably one of the more difficult questions on the exam. And you kind of notice we actually didn't use these probabilities in 12. We actually only used kind of the ones we were given, I guess, plus we had to kind of know how to find the probability of not lying there. But once we identified all the probabilities that we were given, and then write down what you're looking for, the conditional probability you're looking for, use that along with your formula sheet, right? So you can kind of identify what your S and your E are. And then it's just a matter of writing it out in the context of your example, and then it should just be plugging in those probabilities. So those are the kind of steps to take there. All right. Any questions before we keep moving on that? All right. So the next one we'll work through here is question 13. So I'm going to minimize this for just 1 second. So let's say we have this Venn diagram and we're asked for what the probability of B is here. Okay. If we go to our formula sheet, all right, we don't have this equation on there because it's really a combination of two things. So we know that the union of two events can be written out as the probability of both events minus their intersection. So if I look here on this Venn diagram, right, what's in both of these circles, right, this white circle kind of being event A, dark blue circle being event B, what's in both those circles would be the union of those two things. So if I take the area of both of these circles, right, what's in either one of them, and add that to this light blue shaded area, which I'm being told is the intersection of the complements, I know those two things have to add up to 1. So all I'm doing there is saying, I know that entire experimental outcome space is 1. Okay. So if I take the union, or what's in either one of those circles, and I add to that what's outside of those circles, which I'm told, and you'll be told on the exam this as well, is the intersection of the complements, I know those have to add up to 1. Now the trick is here, I know I had that equation on my formula sheet for the union, so I could rewrite this as the probability of A plus the probability of B, but then I have to subtract what I double counted or what was in both those events or the intersection. All right, so this is kind of rewriting the union using that formula from the formula sheet. I then add in, right, I still have this guy here. And now it's just simply plugging in what I know and then a little bit of algebra. So the probability of A is told to us to be 0.4. What we're looking for is the probability of B, so we don't know that. The intersection is 0.2, and the intersection of the complements is 0.1. Right? So 0.4 minus 0.2 is 0.2 plus 0.1, so I'll subtract 0.3 from both sides. I get, what, 0.7 is equal to the probability of B, okay? So the key there was knowing that what's in the area that's in either one of these circles represents the union of those two things, and that because this rectangle represents the entire experimental outcome space, we know the area of that rectangle has to be 1. Well, then the area that's in the circles plus the area outside the circles have to add up to 1. And like I said, the area outside the circles will always be told to you to be the intersection of the complements. So you don't have to worry about kind of remembering that. And then from there, it was rewriting the union of two events. Forgot my mouse today, so I'm using the mouse on my laptop, so I apologize if it's a little slower. The union of two events is just the probability of each event minus the intersection, okay?